So next is voltage regulation calculation. Actually, voltage regulation we have defined already. So there are three methods here we will consider. First one is EMF method or synchronous impedance method. This is the required circuit diagram. Here in this method we will use this OCC and SCC, and since this method is based on the calculation of synchronous impedance or synchronous impedance, so this method is applicable to cylindrical rotor machine only, and we will consider certain assumptions like the magnetic circuit is having constant permeability, which means saturation is neglected, and which will permit us to replace all the MMFs by their EMFs. We have seen the phasor diagram. From the phasor diagram that both space phasor and time phasor EMFs are induced by their corresponding fluxes, which are generated by the corresponding MMFs. So MMFs and EMFs are related, considering that this saturation is neglected. That means they will be that means MMFs and flux will be along the same line, and considering that corresponding EMF will be generated by that flux, and we can consider only that means MMF and flux will be along the same line if we neglect this saturation. So this is the phasor diagram for a cylindrical rotor synchronous generator considering lagging power factor load. So here in this method we will consider this synchronous reactance in having two components. One is armature reaction reactance component, another is armature leakage reaction component, the leakage reactance component. So here this EMF, induced EMF, or the excitation EMF, EF is induced by the flux phi F, which will be ahead of this EF by an angle of 90 degree. So and FF will be in phase with phi F as we have neglected saturation, and current is IA, lagging load, therefore VT, current IA lags VT by an angle of this theta, which is the power factor angle, and the armature reaction MMF, that is FA, which will lie along the armature current IA. So that will be added to this FF because it is phasor sum, so we can displace this FA parallelly, or we can shift this FA parallelly to add with FF, and after that we will get the resultant flux, which is FR. Now here we can see this FA will produce some voltage, or phi A actually. FA will produce phi A, and phi A will induce some voltage, that is EAR, armature reaction voltage, okay, which is actually IAXA. We have seen earlier in phasor diagram that this voltage is equivalent to some reactive voltage drop, which is IAXA. So that induced EMF we can draw here, which also lags this FA or phi A by an angle of 90 degree. So that induced EMF we have to subtract from EF, so that is our ER. So after subtracting this EAR from EF, we will get this resultant voltage, which is the voltage behind the leakage impedance, as ER. Now obviously this ER will be produced by some flux which will lead this ER by an angle of 90 degree. So that flux is phi R, which we will get from FR, which is the resultant of FF and FA. So here FR is the resultant of phi F and phi A. Phi A will be in phase with FA. So this induced EMF EF is produced by phi F, which is produced by FF, This induced EMF ER is produced by phi R, which is produced by FR, and this armature reaction voltage drop that is produced by this phi A, which is in phase with FA, that means it is produced by FA. Okay, so 3 EMFs and 3 MMFs, FF, EF, FA, EA, and FR, ER. We can replace all these EMFs by all these MMFs and vice versa. We can replace these MMFs by these EMFs also. So in EMF method, all the MMFs will be replaced by EMFs. In MMF method, all the EMFs will be replaced by their corresponding MMFs. And this question is IX. So this is our OCC and SCC, and this is the air gap line, which is having the slope as K, and that is the ratio of this MMF and EF. That we will see. And air gap line is a line which passes through the linear portion of the OCC line, OCC characteristic. And we have seen that ZS can be calculated using this formula, or that is OCC, using OCC and SCC by selecting a particular value of field current, and from there we can calculate excess by performing some DC resistance test, or we can directly measure the armature resistance per phase by using some multimeter. Okay, anyhow we have to get this resistance R, and then using this formula we can get excess. So now the EMF method, how we can apply this EMF method. So for lagging power factor load, we can use this triangle, and using Pythagoras theorem we can find this EF, or we can apply this complex calculation method to calculate EF. So here EF as a phasor, we can write Vt plus IaZs, and this Zs value, and Zs value is we have calculated by performing OC test and SC test. Ia will be given to you, mentioning the power factor also. Vt is nameplate data. So this right hand side, all the values are known to you, then you can calculate EF. So here this is the complex calculation you can perform. So here Vt is taken as the reference phasor. So from here we can write this polar form taking Vt as the reference phasor. So angle 0 degree, and Ia lags Vt by an angle of theta. So that is why Ia angle minus theta, and Zs that we can convert into polar form. So this phi is the impedance angle. This phi and theta are not same. And if we consider this triangle, we can directly write this expression using this Pythagoras theorem. So EF square, this square equal to this line square, that is base square, plus this perpendicular square. So base is equal to what? This length, that is Vt cos theta plus IR. So this length is Vt cos theta plus IR, so whole square of that. And this length is this length plus this length. So this length, which is equal to this length, which is Vt sin theta. So Vt sin theta plus IAXS whole square, that will give you, that means this square plus this square will give you EF square, and taking the square root you will get directly EF. So either this using complex calculation or using this triangle you can calculate EF. Once you have EF, Vt is already known to you from nameplate data, so apply that earlier formula to calculate voltage regulation. Now for leading power factor load, again you have the two options. Either you can use this complex calculation or you can use this triangle. Okay, so if we use complex calculation, it remains same, expression remains same, but in case of this triangle, right angle triangle, we can see this sign will be negative. Okay, so here you can see this is EF. EF square is equal to this line square plus this line square. So this line is actually this section plus this section, which is Vt cos theta again plus IR. That is okay. But this length is actually this whole length minus this part. So this whole length is Vt sin theta minus this section will give you this length. So that is why this sign is negative. So actually, if you can remember only one formula, the other one here it will be negative for leading power factor. And for unity power factor, it is very simple. Okay, so Vt plus IAR whole square plus IAXS whole square. That will give you EF. Once you have EF, you can apply this formula to calculate voltage regulation. So this EMF method or synchronous impedance method calculation is very simple. Just you need this OCC and SCC. Then by selecting proper value of field current, you have to calculate ZS. Then if R resistance, armature resistance is given to you, then use that R to calculate XS, or you can perform some DC resistance test to get R, or you can measure the armature resistance simply by using multimeter in resistance measurement mode. Okay. So next is MMF method. Here all the EMFs will be converted into its equivalent MMF. Okay. So how we can do that? So first of all, this is the voltage equation, KVL equation for synchronous generator, and from there we can split this excess into two components. One is leakage reactance, another is armature reaction reactance, and this is the OCC and SCC and the air gap line. So here slope of this air gap line is actually EF by IF. It is obvious. This is EF and this is IF axis. So this slope of this line is ratio of these two, and IF can be considered as equivalent to FF, so EF by FF, which means from this equation we can write EF equals to KFF. That means EF can be replaced by FF using this slope, and in phasor form we can write this. Why this negative sign? Because this EF lags FF by an angle of 90 degree. So if it is true for this EF and FF, it is true for other EMFs and MMFs also. They will follow the same air gap line. So using that concept, we can write this expression. So EF by JK, that is equal to, this is the voltage equation, which is, this is the resistive voltage drop, and the terminal voltage, that is also divided by minus JK, and this part is also divided by minus JK. So what is it actually? Consider this equivalent circuit, the initial one. So from this we can see EF minus JK, and this Vt plus IAR, that is actually this modified induced EMF, and this can be written as, and this XL plus XA, that is FL plus FA. What is this FL? FL is some MMF which can be considered as the induced EMF equivalent to leakage reactance drop only. See, IAXA, that is armature reaction reactance drop, which we have considered as EAR, some kind of voltage drop. So same way we can consider this IAXL as some kind of voltage drop, leakage reactance drop. So if IAXA can be replaced by some MMF FA, so IAXL can be replaced by some similar MMF FL. In that logic, following that logic, we can replace this IAXL by FL. So all the EMFs can be replaced by their MMFs. So here FF, FR1 and this FL plus FA. So basically 4 MMFs, and this 2 will combine as a one single MMF, FL plus FA. And this is the corresponding phasor diagram. So here you can see these are the corresponding MMFs which have produced these EMFs. So first one is ER1, second one is ER, which is equivalent to this FA plus FL. This one is parallel to this one, and EF is corresponding to FF. So EF is replaced by FF, ER is replaced by FA plus FL, and ER1, that is replaced by FR1. Now this angle between FA plus FL, which is in phase with IA, with ER1, that is alpha, which is this angle. Okay.
So here we are taking EMF is leading by 90 degree everywhere.
Because flux, whatever EMF is induced by any flux, that EMF lags that flux by an angle of 90 degree. We have neglected saturation, so flux and MMFs are in phase. So if flux is leading the EMF by an angle of 90 degree, corresponding MMF will also lead by 90 degree. So you have to identify these MMFs. So here FA plus FL is in phase with IA, so that will produce the EMF ER1, and this ER is produced by ER is produced by this FA plus FL, and EF is produced by FF, ER1 is produced by FR1. In that way we will consider. And this angle between ER1 and IA, that is alpha, which is this angle. This angle is important. We need to calculate that angle also. Okay. So we will consider that MMF space phasor diagram only. So this is a triangle where this is the FR1, this is FA plus FL, and we have to calculate this FF. Okay, and this angle is alpha. Now in this calculation, if we take Vt as the reference phasor, it will not give us this angle. If we take armature current only, then only we will get the angle directly. So let me show you. So these are the steps to calculate the voltage regulation using this method. So plot OCC and SCC, find ER1 and obtain the corresponding value of FR1 from OCC. So ER1 can be calculated using that voltage equation only. Vt is Vt plus IAR is equals to ER1, and ER1 you have to find that value in EF axis. Corresponding to that ER1 you have to find the field current value, which is your FR1. Okay, so this calculation you have to take IA as the reference phasor, otherwise you will not get this angle. So here ER1, if you take Vt as the reference phasor, you will get the angle of ER1 with respect to Vt, but this angle alpha, that is angle between IA and ER1. That is why we need to select IA as the reference phasor. This point is important. So take IA as the reference phasor. So that is why when you take IA as the reference phasor, Vt will be ahead of IA by this power factor angle. So here theta is positive. Angle of IA is 0. Then find FA plus FL from SCC, that is this value is corresponding to rated armature current value or whatever armature current value is given to you at which you want to calculate the voltage regulation. So from that you will get FA plus FL value using SCC. So after getting this FA plus FL and this FR1, so this one and this one are known to you, so you have to calculate FF. So you can apply this trigonometric formula to get FF. So this is the formula to calculate FF. This square plus this amount, which is the sine component of this length, plus cosine component of this length, that length will give you FF square. So if you take square root of this, you will get FF. So after getting FF, using OCC, you will get the corresponding EF directly using OCC, that means plot. So after getting EF, the formula remains same. Okay. Okay, I will discuss this one. Before that, let us go through how we can use this to solve problem. Wait, is it? Open the folder. Full screen mode, slideshow. Okay, so this is a problem to calculate voltage regulation for by different methods. So first one EMF method, MMF method, zero power factor method. Okay. So here a 220 volt 50 Hz 6 pole star connected alternator with ohmic resistance 0.06 ohm per phase. So resistance is given, no problem. We have the following data on open circuit, short circuit and full load zero power factor characteristics. So three characteristics are given. So this is the field current values, this is open circuit value, that these are line values, this is short circuit current, star connected. So line current and phase current will be same, and this is zero power factor terminal voltages. So this is also line value, so you need to convert in phase. Okay, so first of all let us follow this EMF method. So this is the corresponding phase values for this voltage, and short circuit current will remain same. Okay, so we will plot this one versus this one and this one versus this one. So this is the plot. If we plot those data, we will get this OCC and SCC. So this is EF axis in volt and this is ISC axis in ampere. Okay. So how to calculate ZS? We have to select one field current value. So let us select this value. F is equals to 2.3. So from this point you have to draw one vertical line which will intersect OCC as well as SCC at two different points. So this is the intersecting point of SCC, this is the intersecting point of OCC. So from OCC draw a horizontal line that will intersect EF axis at some point. So identify this voltage. And from this point draw another horizontal line that will intersect ISC axis at some point. So identify that current. So this voltage is 156 volt, this current is 76 ampere. Take the ratio of these two, you will get ZS. That's it. Okay. So here ZS equals to 2.05 ohm and R is given, so you can calculate XS. So XS is calculated as 2.05, almost same as that of ZS because RA is very small. Okay. So once we get this RA and XS separately, we can write this ZS in complex form and we can convert it into polar form. We will be requiring this polar form. Okay. So now we have ZS. So we have to calculate this voltage regulation at rated full load current, that is 40 ampere at 0.8 power factor lagging. So power factor and full load current is given, both are given. Okay. So here we will take Vt as the reference phasor. So Vt equals to, this is line value, so we need the phase value, and Ia is given 40. So power factor is 0.8 lagging. So corresponding angle is either you can find the corresponding angle and you can write cos theta or sin theta. Actually cos theta value is this, from there you can find the sin theta value, it will come this. Okay, and as it is lagging, so this sign will be negative. Or you can write, after getting the power factor angle, 40 angle that 40 angle will be cosine inverse of this with a negative sign as it is lagging. Okay, so that's it, 40 angle minus of 36.87. Okay, so therefore EF calculation using this complex method. So this is Vt angle 0 degree, and which we can write as Cartesian form like this, and this one we will do this multiplication in polar form because this into this will give you the magnitude and this minus this will give you the corresponding angle. From there you can convert this into Cartesian form to get the final value. So EF will come like this, and once we have this EF magnitude, apply this formula to get voltage regulation. Very simple. Any doubt, any question? So next we will go for the second method, that is MMF method. So for MMF method we require the same two characteristics. So this is open circuit data, power phase values, and this is short circuit current, that is power phase line voltage same, line current same because it is star connected alternator. So again, So per phase terminal voltage and armature current is given this, power factor is given this. So this is the phasor diagram which we need to calculate this voltage regulation by MMF method. So here we have to take IA as the reference phasor. This one is important. If you take VT as the reference phasor, you will get this angle. Okay, this angle between VT and ER1. Okay, so in that case, you have to calculate this alpha by somehow in any other way. So which is extra load. We cannot do that. I mean, we will not do that. We will take IA as the reference phasor. So here we will calculate ER1 taking IA as the reference phasor. So whatever ER expression we will get, the angle will be angle between IA and ER1. Okay, so that is why here we will take IA as the reference phasor. So now I taking IA as the reference phasor, this angle will be 0 and angle of VT will be plus theta, because VT is theta degree ahead of IA. So beta will be 36.87 degree. We have seen this. So taking this, we will calculate this voltage behind the armature resistance, that is ER1. So this will give you some value. Okay, so this volt. So now go to your plot, identify this voltage in EF axis. Draw some horizontal line that will intersect OCC at some point. From that point, draw a vertical line to get the corresponding FR1. Okay, so this voltage 129 approximately. So this will give you FR1. So this is 1.7 ampere. So FR1 at ER1 equals to 129 volt is 1.7 ampere. So 1 mmf is calculated. Now we need next one, FA plus FL. So how to do that? This you can calculate from armature current value. So armature current rated value is 60 ampere. So from there you draw one horizontal line which will one horizontal line that will intersect SCC at this point. So from this point you need to draw one vertical line that will give you FA plus FL. So 1.2 ampere. So that is your FA plus FL. Okay. So this is the field current which is required to circulate full load short circuit current. FA plus FL. So now we have FR1 and FA plus FL. Now recall that MMF phasor. Use that triangle to calculate FF. So this is the triangle. So again you see this alpha we have already calculated while calculating ER1. Automatically it is calculated. You don't have to calculate it separately. That is why we need to select IA as the reference phasor. So now using this triangle we can calculate FF. So calculate FF. 2.6 ampere. So again go to your plot. Identify this ampere in field current axis. From there draw one vertical line that will intersect OCC at some point. So this is 2.6 ampere. Draw a vertical line that will intersect at some point. From here draw a vertical line that will intersect EF axis at some point. That is your required EF. Automatically it will come. So this is your required EF. Once you get EF, apply the formula to calculate voltage regulation. Very simple. Just you have to follow the steps. So from OCC, EF you have got 164 at field current 2.6 ampere. So after that, apply that formula. So that is the voltage regulation. Any doubt? Any question? This Z power factor method, zero power factor method, that is little bit lengthy and little bit complicated. So that I will discuss first, then we will solve. And go back to previous slide.
This one.
Yeah.
Sir, in EMF and MMF method, in MMF method we will replace MMF by EMF.
Yes.
So, but the MMF phasor F will be replaced by E.
FF will be replaced by EF.
Okay, that phasor only. Okay.
Okay, so this is the last one to calculate voltage regulation. So zero power factor or Pottier reactance or Pottier triangle method. So this is also called the general method of obtaining the voltage regulation of an alternator, and this method will give you more or less correct result. I mean most accurate result. So this is the phasor diagram, corresponding phasor diagram. Here you can see, here we will be using ER, EF, and this armature, leakage reactance, IAXL. Okay. So from the general phasor diagram, we can write the expression to calculate ER. So ER equals to VT plus IA into R plus JXL. Now the problem is you cannot calculate ER because VT is known, okay, IA is known, RA is known, XL is not known. That is your first problem. You cannot calculate ER. If you cannot calculate ER, how you will get FR? That is the problem. Okay. So for that, while you will be calculating this, you have to take IA as the reference phasor. Reason is same. This angle between IA and ER, that is beta, that will come automatically. Okay. So that is another point we will discuss later. First of all, here problem with this equation is you cannot calculate ER because XL is unknown. XS is known. XL is unknown. So how you will get XL? So this is the zero power factor phasor diagram, if you can remember, and this is OCC and ZPFC. So here VT is known to you, per phase value, so you can draw one horizontal line and that will intersect ZPFC characteristic, zero power factor characteristic at this point, and you will draw a line which is equal to OF dash, this length, this amount of field current. Okay, you have to draw one line from this point, which is the intersecting point of VT and this zero power factor characteristic. So that is the rated value point, you can say. Okay, so from here you have to draw this line which is equal to OF dash, some amount of field current value. Okay, and now you have to draw the air gap line. So draw this air gap line and draw one line from this point which will be parallel to this air gap line, and that will intersect the OCC at some point. Okay, so and that point will be this ER. Okay, and from phasor diagram we can see, though it is drawn like this, but actually this IAR drop is very small, and this IAXL, this drop is almost perpendicular to IA. So we can consider this length is IAXL. We need IAXL actually. We don't require XL separately. We need only IAXL as a product. That will serve our purpose. Okay. So here now we will join A and C, and we will drop one perpendicular on AB or AD from C. So that length BC is equal to IAXL actually, and AB length is actually FA, armature reaction. So here BC length is IAXL and AB length is FA. So from the value of ER, now once we get this IAXL, we can calculate ER, and using OCC we can get the corresponding FR. The process is same. Just we have to find the ER value in this voltage axis, and then we have to draw one horizontal that will intersect some at some point on OCC, and drop one vertical line on field current axis. You will get the corresponding FR. Same process. Okay. So either you know FR or ER, you will get the corresponding value. If ER is known, you can find FR. If FR is known, you can get ER from using OCC. So that is your FR. So OF equals to FR, and armature reaction. So draw one vertical line from this point, and that will intersect OCC at some point. So OP is actually this EF PF, that means from this point to this point, that is FA. Why? Because this length is FF, which will give you the EF line if you draw that horizontal line, not required here. So OP is equals to FF, and this OF, if you subtract that OF from OP, you will get this length AB, which is FA. So PF or AB, that length is FA. So from Portier triangle, you will get FA directly. And once you get FA and this FR you have got from ER value, so you can calculate FF. Once you get this FF, I mean this using this formula or using this triangle, either way you will get FF. Once you have this FF, you will get the corresponding EF from OCC. So that is FF calculation, and voltage regulation calculation is this. Okay. So go back to previous slide, previous PPT. That numerical. Yeah. So ZPF method. So follow the steps carefully. So we need OCC as well as ZPF. We don't require ACC here. So we will plot ZPFC and OCC to apply this method. Before that, let us calculate the regular data. So VT, IA, and again you have to select IA as the reference phasor to get this angle beta directly. So IA is taken as the reference phasor, VT is taken ahead of IA by an angle of 36.87 degree. So voltage behind leakage impedance will be calculated using this formula, taking IA as the reference phasor, but we don't know this IA XL or XL, so we need these two plots. So first of all, this is the air gap line and this is the VT value. See, 127 volt, that is the VT rated value per phase basis. So draw this line. So this is your one corner of Portier triangle. And now equal to this length, draw this line. So that is AD, base of Portier triangle.
So AD equal to OF dash.
OF dash, correct. And draw this DC, which is parallel to air gap line. So you have this point now, and join AC, and then drop this CB perpendicular, or drop this CB perpendicular and then join AC, no problem. So here ABC is the Portier triangle, not ADC. ABC is the Portier triangle. So here this BC length is IXL and AB is FA. So draw a horizontal line from this point on, and that will intersect EF line at some point. So this point, identify that point. So that is 157 volt. You have to draw this horizontal line considering this length. Okay, so this is one voltage which is corresponding to this point. So draw, identify this voltage. Now take the difference of this volt and this volt. That will give you IAXL. So from Portier triangle, armature leakage reactance drop BC, which is IAXL, is 157 minus 127 volt. So now you have IAXL. Now you can calculate ER directly. So VT plus IR plus this is equal to 30 volt. So calculate ER. Sorry. So here this angle is beta in that MMF triangle, and this is the voltage ER. So from ER value, so find out that 148 volt. So this is the 148 volt. Draw a horizontal line here, which will intersect OCC at some point. From that point, draw a vertical line that will give you FR. So find FR. So FR equals to 2.1 ampere. So 1 mmf is calculated, 2.1 ampere. Okay. Next one, this one. So draw one vertical line corresponding to this B point. So what is this value and what is this value? Identify from this axis. Okay. So here one field current value, here one field current value. Take the difference, you will get this PF, which is equal to AB, which is equal to FA. So that is 3.26 and this one is 2.4. Take their difference. So armature reaction MMF AB equals to FA equal to difference of these two, that is 0.86. So now you have FA as well as FR. Use that MMF triangle to calculate FF. So FF will be using this triangle. This is the formula, and beta you have already calculated while calculating ER. So this will give you 2.8 ampere. Now go to that plot. Identify 2.8 ampere on field current axis. So this is your 2.8 ampere. Draw a vertical line that will intersect OCC at some point. So that from there draw a horizontal line and find that voltage. So that is 169 volt. This is your EF. So FF is converted into EF. So now EF is 169. Again apply that formula. So that will give you the voltage regulation. So any doubt, any question?
You want to take deep breath?
If all of you want,
Sir,
yes.
there are two voltage regulations. One is VR up, VR down. Voltage regulation up and voltage regulation down. So both can be found out here in this case.
VR up and VR down.
Yes. I
No,
mean,
no.
169 minus 127 by 127. One. Another one is 169 minus 127 by 169.
No, that is according to different authors. Formula can be any one. Normal standard formula is this. In other book you will find some other formula. No problem. Concept remains same. In different books you will find different formula.
Especially voltage regulation up and down, that is followed in our transformer case. Not in alternative case it is positive or lagging like this. Otherwise it will be
No, if the power factor is leading, in that case this EF will be less than that of BT.
negative.
In that case you will get
The
negative voltage regulation.
up and down. Up and down will be
Transformer.
transformer. It will be a positive.
Negative voltage. No, calculation method is clear?
Ah, it is here.
So, break will be good
5
now?
minutes break.
Okay.
5 minutes break.
Okay.
Sir, if Portier triangle is there, can we draw the ZPF from Portier triangle? By just shifting it.
Just shift it downwards. Following, keeping its tip on the OCC line.
So there is a problem in some semester. How to draw it? How to draw this?
If you have the Portier triangle, you can draw the ZPFC by shifting it downwards, keeping its tip on OCC.
Sir, if you not draw the ZPFC, only the initial point you take.
Yes.
Can you draw parallel to OCC, ZPFC?
It is little difficult. It is point, rated point. That from there also you can draw the ZPFC.
During doing experiment, it is difficult to take all readings of ZPFC.
Obviously. बैटरी मुझे लग रहा है खत्म हो गया।
पूछ लेता हूँ सर से।
अभी तक चल रहा है लेकिन मुझे लग रहा है खत्म हो रहा है।
अच्छा,
डिमिंग दिखा रहा
MMF method, suppose this is the EMF, this is the EF, and we negative lag is FF, and the EA will be some, EA will be EF, EA will be somewhere, so according to the direction of IA. So in MMF and EMF method, what is the difference that you have?
EMF method ZS is calculated. You don't need actually this direct relationship between EF and FF.
Okay.
But so in MMF method you need this relation because you have to replace all the EMFs by their corresponding values.
This FF will be replaced by EF. Okay.
No, EF will be replaced by FF.
EF will be replaced by EF. So
Because-
FF will come here.
No. Replace means corresponding. Suppose you have calculated FF. So you have to find the corresponding EF value from this FF value. So you will calculate this FF value using that triangle. Now you know this point. So draw a vertical line that will intersect OCC at some point. From there you draw this horizontal line. This will give you EF. So which means from FF you are getting EF.
FF we are getting EF, but this value what we get, that is EF value only, na? That we cannot replace by FF.
No, not required.
Replacing means what?
VR is
EF minus VT by
EF minus VT by VT.
VT.
So that remains same. Anyhow you have to get EF.
EF from the value of FF.
In MMF method you are getting this EF from FF.
Okay, EF from FF, but no replacement of one variable with other variable.
No.
That was it.
Replacement means just following the same mathematical relation you are expressing EMF EF with other two EMFs, here FF with other two EMFs. That is the replacement.
This one is given in the book.
In Vibra's book, but in Vibra's book,
Vibra
too many things are.
written.
So it is a little bit difficult for Kothari's book I got. Kothari's book actually copied from this. Vibra's book is also copied, but first hand
copy in India.
The actual book is written by P.C. Shen. That book is also available in internet. You can find P.C. Shen. P.C. Shen's
345 minutes support paper IEEE paper presentation
oh, that you can ask you ask the who is coordinating that Pawan sir or some other. You take permission from them. I am there. चेंज कर दो हाँ ये ट्यूटोरियल छोड़ के वो पहले वाला जनरेटर सिंक्रोनस जनरेटर जो
ହେଲା मैकबुक चार्जर सर बहुत फायदा गोटे चार्जर सब चार्ज लैपटॉप आईफोन आईफोन भी सपोर्ट कर सर पिला कौड़े गले पढ़े आसे
Shall we start? Okay, so next is two reactance concept of salient pole synchronous machines. That is Blondel's two reaction theory. So first of all, we will see that whether this two reaction theory is required to explain the operation of synchronous salient pole synchronous machine. Then we will explain that theory. Okay. So Blondel's two reaction theory. So first of all, in EMF method of voltage regulation, we have seen that armature reaction MMF FA is accounted for by means of an equivalent armature reaction MMF EA or EAR. We have seen this, right? So FA will produce phi A, that phi A will induce this EMF EA, which is actually some reactive voltage drop as IA XA. Okay. So the point is here this armature reaction MMF will be accounted for by this equivalent armature reaction MMF EMF EA, and this EA is considered as a reactive voltage drop in fictitious reactance XA, and from there the concept of the overall excess is evolved. That means synchronous reactance is the sum of two reactances. One is the leakage reactance, that is the machine's own parameter. That means due to leakage in the armature, there will be this reactance XL, and this due to this armature reaction, there will be another reactance which is XL. Sum of those two will give you XS. So only one reactance is okay for this machine. So from there, this is permissible in a cylindrical rotor machine. That means in cylindrical rotor machine, only one reactance is sufficient to explain its performance behavior. Okay. Now, so here we can see that if we neglect these slot openings, the air gap is more or less uniform. So if the rotor rotates, the air gap length will not change. See, the air gap is uniform and the reluctance of the magnetic circuit is constant, and it does not vary with the position. That means with the rotation of this rotor, that means whether this end pole position is here or here or here, it doesn't matter. It will offer same reluctance to the armature MMF. So we will have only one reactance. Consider this rotation animation. So see, this is suppose end pole and this is S pole. So whatever may be the position of this end pole, doesn't matter. This air gap, whatever flux is there in the air gap, resultant flux, that remains same. So that is why only one reactance is sufficient for cylindrical rotor type machine. But that is not the case for salient pole type machine. For the case of salient pole synchronous machine, the situation is totally different because we are having different length of air gaps along the polar region and the interpolar region. So here you can see along the polar region, this air gap length is much smaller than that of this air gap length in the interpolar region. So if the rotor rotates, when the rotor rotates, see, whatever conductor, consider this conductor C dashed. So whatever reluctance it is experiencing now, that will be different after a certain time interval. This rotor will acquire the position here, so air gap length will be lesser. When it passes and comes under this section, the reluctance will be different. So at every instant of time, the reluctance offered due to this variation in air gap length will be different. So we cannot explain the performance by considering only one reactance. We will be requiring two reactances. So the armature reaction MMF cannot be accounted for by one equivalent reactance only. So this is because the air gap is not uniform, the reluctance of the magnetic circuit along the polar or direct axis. That means along this line or this line or this line or this line. That means we will consider one center point of one pole as the direct axis or the polar axis. It is very small, and the other one, that is interpolar axis or quadrature axis, in quadrature with this d axis or direct axis or polar axis, air gap length will be more. So you can see this animation. So air gap length in this polar region or here on the south pole, that is very small, but in interpolar region it is very big. So we cannot explain its performance by considering only one reactance. So that is the point of having two reactances in salient pole type machine. So now we will see how these two reactances can be obtained. So first of all, this is the d axis along this north pole or the pole axis, and along this direction, that is the interpolar or the q axis. So along this d axis, the field MMF will be there, that is FF, and the corresponding flux phasor phi f, considering this no saturation is there, and the field poles NS on rotor are shown facing the coil sides A dash. So again we will consider similar situation like we have considered in cylindrical rotor machine. So at this situation, at this instant of time, this north pole is giving maximum flux to this conductor side A, and this conductor side A dash is facing maximum flux produced by south pole. So these two conductors will have their maximum induced EMF at this instant of time. So that is maximum EMF situation. Now for an anti-clockwise direction of rotation, the direction of induced EMF will be along this line, along the axis of pole, along the axis of this conductor A and A dash, so which is in quadrature with phi f or FF. So we can draw that EF along that line, but before that we will consider that if the machine is loaded, in that case what will happen? Depending on the load power factor, this EF will lead or lag, depending on the power factor, the current, armature current from this EF by that power factor angle. So during that period of time, this N pole and S pole will move ahead by that angle, as we have seen in case of cylindrical rotor machine. So suppose the power factor is lagging and the angle of power factor is suppose psi degree. So in that case, this A dash, these two conductors will have their maximum current when during that period this N and S pole will move through that angle psi degree. So the next position will be like this. So after this earlier situation, the N pole and S pole have moved by this angle of psi, that is the power factor angle for this case, and now the situation is this conductor A and A dash will have their maximum current, not the EMF. EMF will be maximum, the conductors which will be here and exactly facing the north pole and south pole. So that the point is how many degrees it will travel so that this maximum EMF conductors will now have its maximum current. That depends on the power factor angle. If it is purely lagging inductive load, then after 90 degree. If it is in between, then that depends on the inductance value. Okay, so that is the point. Now if we consider this situation, so here EMF is not maximum now at this conductor A and A dash, current is maximum. So in this situation, what will be the direction of that current MMF, IA or FA? It will be along the axis of this IA, A and A dash. So let me draw that. So that is the direction of FA. Okay, so this is the direction of FA now. Now see, this FA, it is neither along D axis nor along Q axis. It is somewhere in between, and this position depends on the value of psi. Okay. So if we change the internal power factor angle psi, then the position of this N and S pole will be different, and based on that, if we resolve this FA or IA into two components, one along D axis, another along Q axis, both of them will see different reluctance. Am I clear or not? If we resolve this FA, one will be along this line, another will be along this line. So this, the component of FA which will be along this line, that will face reluctance due to this maximum air gap, and this along this line, whatever may be the component, so that component will face the reluctance due to this small air gap. Okay. So here, as this reluctance shown by the current, armature current or armature MMF FA will be different, and that will be dependent on this power factor angle psi. So we cannot explain this concept or this theory by whatever we have used in cylindrical rotor machine. That is why we need this two reaction theory. So we will express this FA and FA into two perpendicular components, and they will face to different reluctances, and those two reluctances will be constant. One along minimum air gap path, another along maximum air gap path. So that we will see. So first of all, according to this two reaction theory, this FA will be resolved into two components. One along D axis, that is FAD. So that is the D axis component. Another along Q axis, that is FAQ. So FAQ. So component of FA along D axis, along Q axis. You can see this, whatever may be the position of this rotor, this reluctance seen by FAD is constant and it is minimum. It is for the minimum air gap length, and reluctance faced by FAQ, that is also will remain constant whatever may be the rotor position, and it will be due to this maximum air gap length. It does not depend on the rotor position. Whatever may be the rotor position, that will remain same. Now, so FAD is magnetizing if psi is an angle of lead. That we have seen in earlier cases. This armature reaction, it can be either magnetizing, demagnetizing, or cross magnetizing based on the power factor, based on the load connected. If it is leading load, it will be magnetizing. If it is lagging load pure, in that case it will be demagnetizing, and in case of unity power factor load, it is simply cross magnetizing, which will distort the waveform.
So the angle psi is the angle of the load.
Here it is considered as angle between EF and IA. Like previous case, we have ignored the impedance drop. So here one component is magnetizing, another component is cross demagnetizing, and FAD is magnetizing if it is angle of lead, it is demagnetizing if it is lag, and FAQ will produce only cross magnetizing effect, and that will distort the field flux, nothing else. Okay. So now we will draw the phasor diagram. So steps are very important. So first of all, D axis and Q axis are drawn. So this is the field MMF, EF will be induced by this field MMF or field flux. So that is phi F along the same line, neglecting saturation, and this is the EF. So if we consider lagging power factor load, so I will be drawn lagging EF by some angle, and VT, IA will also lag VT if we consider this impedance drop is there. So now angle between VT and IA is theta, angle between EF and VT is delta, that is the load angle, and angle between IA and EF, that is called the internal power factor angle. That is sum of theta plus delta in case of lagging load, and if the angle is, if the load is leading, in that case it will be, psi will be theta minus delta. In case of unity power factor load, delta and psi will be same. So here lagging load. So now psi is delta plus theta. Now resolve IA into two components. One is ID along D axis, and another is IQ along Q axis. So two components of current, armature current, ID and IQ. So these two currents will face two different reluctances, one along D axis, another along Q axis. Now draw FA along IA, and it will have again two components. One is FAD along D axis, another FAQ along Q axis. So FAD is due to ID and FAQ is due to IQ. So FAD is produced by ID, FAQ is produced by IQ. So what is this ID? ID is the sine component of that psi, which is theta plus delta. So I sine psi is equal to ID, and I sine IA cosine of psi, that will give you IQ. Okay, so two currents. Now phi A is drawn, it is not in phase with FA or IA. That is the difference with cylindrical rotor machine. We cannot draw phi A in phase with FA because here two reactances are there. Okay, so phi A again resolved into two components, that is phi AD and phi AQ. And why we cannot draw phi A and FA or IA in phase? Because phi AD is equals to FAD by SD, and sorry, phi AQ is equal to
Sir, here.
FAQ by SQ. So what is this SD and SQ? SD is the reluctance along D axis, SQ is the reluctance along Q axis. Now here SD is less than SQ because their air gap length is different. Okay? Along D axis air gap length is less, along Q axis air gap length is more. So since SD and SQ are different, therefore FAD and FAQ are not also equal, and this ratio are also not equal. That is why we cannot draw FA and phi A along the same line. Okay? So hence FA and FAQ are not in phase because they are facing two different reluctances along two different directions. So neglecting saturation, EAD, the armature induced EMF due to D-axis armature MMF component FAD can be written as this one. See, the logic is same. Earlier we have used this concept. In case of cylindrical rotor machine, it was EAR is equal to minus of JK FAR. Armature reaction MMF to armature reaction induced EMF. So here as we are having two components, so two equations will be there. So EAD equals to minus of JK FAD, and which can be replaced by the CKD, which is actually some reactance XAD. So we can write this as XAD. So this reaction, okay. FAD, that can be written as KD into ID. Similarly, for Q axis, we can have similar expression, that is EAQ is equals to some voltage drop, which is XAQ IQ. So we have to add these drops, or we have to subtract these drops from EF to obtain VT or to reach VT. Okay, so we will do stepwise, because still after subtracting these we will have to subtract this leakage reactance drop, then armature resistive drop, etc., etc. Okay, so here XAD and XAQ are respectively the D axis and Q axis magnetizing reactances or armature reaction reactances. In cylindrical rotor it was only XA. Here it will be two, XAD and XAQ. So now we can write this voltage equation. So ER equals to EF plus EAD plus EAQ, which these two can be replaced by these two negative voltage drops. That means from EF we are subtracting those two reactive drops to get ER. That means voltage behind the leakage reactance.
So C and KD are some constants.
Yes. Okay. So after subtracting these two drops from EF, we will get this voltage ER, which is voltage behind the leakage reactance. Okay. Now we have this XL and IAR, R. So if we subtract all those two drops, then from ER, then only we will get VT. So here IAR drop and IAXL drop are subtracted from ER to get this VT. Now here you can see these two drops are with respect to their corresponding current ID and IQ, but these two drops are for the whole current IA. So we have to again resolve this IAXL into two current components drops, ID and ID and IQ, and then we have to add those two with those two components of armature reaction drop. Then only we will get the total reactance along D axis and Q axis, that is XD and XQ. So minus JIAXL, that IA is resolved into two components, ID and IQ, and now we have two reactive drops, two leakage reactive drops, one for ID, another for IQ. IDXL will be added to IDXAD, IQXL will be added to IQXAQ. So these two are added. So the modified phasor diagram based on this modification in the voltage equation will be like this. So see, this is XL IQ added to XAQ IQ, and this is XL ID added to XAD ID, and IAR that remains same. So after that we can combine those two, that means XAQ plus XL is replaced by XQ, XAD plus XL replaced by XD. So now we have one reactance, here also we will be having one reactance. So this is the modified phasor diagram containing two reactances XD and XQ, which contains both armature reaction and leakage reactance in two different directions. Okay, so XD is XAD plus XL, XQ is XAQ plus XL. Okay, so in this way we will get two different reactances. Okay, so XAD plus XL, that is XD, which is known as the D axis reactance, and D axis synchronous reactance, and XAQ plus XL, that is XQ, which is Q axis synchronous reactance. Okay, So therefore, the simplified version of phasor diagram will be like this. Only showing the main components. No space phasor, only time phasors. No flux, no MMFs, only time phasors. This is the simplified phasor diagram for salient pole machine. For a lagging power factor load. You can practice for leading power factor load also and unity power factor as well. So this is the voltage equation. So any doubt, any question? Clear? So next is slip test. So why do we do slip test? To determine this XD and XQ. In case of cylindrical rotor machine, we have OC test and SC test to determine this ZS and XS. Here to determine XD and XQ, we will perform the slip test. Okay, this test is very interesting. We will run the synchronous machine as a induction motor using the induction motor principle. Okay, let us see. So determination of XD and XQ. So this is the experimental setup. Here the field winding will remain open circuited. Only a voltmeter will be connected. That means field winding will not be excited. No DC supply will be given to the field winding. Armature winding through some auto transformer, 3-phase auto transformer, that is variac, we will apply AC voltage to the armature winding. One voltmeter and one ammeter will be connected to record the readings. Okay. So how we will run this machine? Since no excitation is given to the field winding, so this machine will not generate electricity. That means it will not run as a generator. Okay. So what will happen then? First of all, a balanced 3-phase voltage much less than the rated voltage is applied to stator coils of the salient pole machine through a 3-phase auto transformer variac. So we will apply some voltage across the armature terminals, though at a reduced level. Then field terminals are kept open and no supply is given to it. See, it is open circuited, only a voltmeter is connected, which is equivalent to open circuit. Now, its rotor is rotated by a prime mover in the forward direction. So rotor will be rotated by some prime mover at what speed? Not at synchronous speed. Either slightly below synchronous speed or slightly above synchronous speed. Why we will do that? We will create some slip with what? With the rotating field MMF, which will be produced in the armature winding as we have applied some AC voltage. Okay. So at a speed slightly less or slightly more than synchronous speed, rotor is driven by some prime mover, maybe some DC machine, DC motor. So since there is no supply in the field, there is no field flux, so no induced EMF in the armature. So in armature there will be no induced EMF, that is true, but we are supplying some AC voltage, so voltage will be there in armature. So stator supply voltage and current are measured by a voltmeter and ammeter. So what voltage we are supplying, that will be recorded by this voltmeter, and what current it is drawing from the supply, that will be recorded by this ammeter. Okay. Now a voltmeter is connected across the field terminals. So why this voltmeter is required? See, we are producing some rotating magnetic field in the armature which will rotate at synchronous speed. But we are driving the rotor at a speed which is not synchronous speed. So there is a relative motion between that field winding and the rotating magnetic field. So there will be some flux cutting action. There will be induced EMF in the rotor field winding. How much voltage will be there? That voltage will be recorded by this voltmeter. So induced EMF will be there in the field winding, not in the armature winding.
So because of the flux of the input
voltage is given to armature winding.
Yes, sir.
It is producing this rotating
flux.
magnetic field which is rotating at synchronous speed. Rotor is not moving at synchronous speed. It is driven at some speed other than synchronous speed, maybe less, maybe more. Okay. So point is there is a relative motion between that rotating magnetic field and the rotor. So due to that relative motion, there is a flux cutting action. So induced EMF will be there in the in the field winding. Okay.
Whose frequency will be S into X.
That we will see later. Induced EMF will be there. Okay. So point is induced EMF will be there in the field winding, not in the armature winding. Up to this, okay. And that induced EMF will be recorded or can be seen by this voltmeter. So now when a three-phase supply is given to the three-phase stator coils, a rotating magnetic field is developed in the stator and rotates at synchronous speed, as I have mentioned, and rotor is rotated at some speed which is not at synchronous speed. Okay, and the RMF thus passes slowly at slip speed. Okay, so what is the relative speed between this rotor and the RMF? That is the slip speed difference between NS and NR. Okay, so there will be induced EMF in the rotor field winding and it will produce this induced EMF which will have the frequency of SF, slip frequency. Okay, so RMF rotates at relative speed of NS minus NR or NR minus NS if it is more with respect to rotor salient pole structure called the slip speed. And if we assume the rotor to be stationary, the RMF is as if it rotates in with this speed NS minus NR or NR minus NS. So point is there is a relative motion and due to that AC voltage will be available across the field winding and that can be seen by this voltmeter connected across that field winding. Okay, so that is the situation. So this is the waveform of rotor voltage. AC voltage will be generated and the frequency of this voltage is SF. Okay. Now the stator, however, continues to draw current from supply at 50 Hz. State armature that will draw some current from the supply system, and that current is also at 50 Hz. Okay. So this is the current waveform. Let us assume that it is the current waveform for the time being. It will not be like this. It will be something different. Okay. So point is its frequency is 50 Hz. So whatever current the armature is drawing from the supply, that current is having a frequency of 50 Hz. Rotor voltage, rotor induced voltage have a frequency of SF. Okay. Now the magnitude of this stator current cannot remain constant. This is important. Why it cannot remain constant? Because the rotor has saliency. It will see different reluctances at different instant of time. So when the armature current sees the reluctance across D axis, that is minimum. So if the reactance is minimum, current will be maximum. If the reluctance is more, XD, the reactance is more, current will be less. And as the magnitude of current varies, there will be voltage drop in the line due to this line impedances. So that VT, whatever we are supplying, that record of voltmeter connected across the armature terminals, that voltage reading will also change due to this variation of magnitude in armature current due to different reactances. Okay. So when the RMF is along D axis, the reluctance is minimum. Thus to produce same flux, current required is less. So it will draw lesser current. Thus supply current magnitude is less when the stator MMF is along D axis. Okay. So and when the RMF is along Q axis, the reluctance is maximum. Therefore to produce same flux, current requirement is more. Therefore the supply current magnitude is more when the stator MMF is along Q axis. That can be seen from this diagram. So see. Okay. So when D axis, the current requirement is less. When along Q axis, current requirement is more. Okay, and this frequency of this armature current that remains 50 hertz, but the envelope of this variation of magnitude of current that will have a frequency of 2SF. Okay, so you can see frequency of this envelope that is having a frequency of 2SF, double the frequency of this rotor voltage. Okay, and now as the current varies, there will be different amount of voltage drops, so that voltmeter reading will also change. Okay, so what will be the voltmeter reading? When supply current is more, voltage drop will be more, so reading of that voltmeter will be less. And when the supply current is less, so this thing here, current is more, voltage drop is more, so voltmeter reading will be less. And along D axis, current is less, voltage drop is less, so voltmeter reading will be more. Okay, so the supply voltage is less along Q axis, and when supply current is less along D axis, voltage drop will be less, so voltmeter reading will be more. Okay, so in that case, this is the variation of voltage. See, when current is more, voltage reading is less. When current is less, voltmeter reading is more. And its variation follows the same variation of that armature current. That means this envelope will have a same frequency of that of envelope of armature current. That is 2SF. Supply frequency will remain same. That is 50 hertz frequency. I mean, frequency of this current and voltage will remain same as that of supply frequency. Frequency of this rotor voltage is SF. Frequency of envelope of current and voltage across armature or through armature, that is 2SF. Okay, is it clear? Now from this we can take the reading along D axis, that is minimum current, maximum voltage, along Q axis, maximum current, minimum voltage. If we find the ratio, we will get XD and XD. So assume the machine to be a star connected, so XD will be Vt max by √3 divided by A minimum. It is star connected. So along D axis, this voltage, that is line voltage, divided by √3 will give you phase voltage divided by this minimum current. So that will give you XD, and XQ will be Vt minimum by √3 into Ia max, these two. So current is maximum and voltage is minimum. So Vt minimum divided by √3, that will give you phase voltage, divided by Ia max, that will give you XQ. Clear? Any doubt? So from this, can you guess which one will have larger value, XD or XQ?
XD.
Obviously XD.
Sir, you have to fill this. On the last of the session, end of the session, you have to fill this.
So, shall I continue or you want break? Continue. Okay. Okay, so that is last topic, power equations and power angle characteristics. So last topic.
Yes.
5 minutes. Break in what?
Okay, no problem. So power angle characteristic. So neglecting armature resistance, alternator equivalent circuit can be drawn like this. If there is no armature resistance, this is the equivalent circuit, and what will be the phasor diagram? This will be the phasor diagram. Okay. So no armature resistance drop. Directly this reactive drop, which is perpendicular to armature current. So this is the phasor diagram for when we neglect the armature resistance. Now using this phasor diagram, we will derive the power angle characteristic. So if we have considered lagging load, therefore Vt taken as the reference phasor. So Vt equals to Vt angle 0 degree. Ia, it lags Vt by an angle of theta. So Ia phasor equals to Ia angle minus theta. Therefore Ef, which is Ef angle delta. See, Vt is the reference phasor. Ef leads Vt by an angle of delta. That is why Ef can be written like this. Ef phasor equals to Ef angle delta. That have you got that?
Yes. Just use this vector. Okay.
So here a perpendicular EF is drawn from Vt. So this is the perpendicular drawn from Vt. So here this angle is theta, this angle will also be theta, because this one are 90 degree, and this angle and this angle are opposite angle, they are same. So this one same, this one same, so third one will be same, right? So this angle is theta. So now we can write this EF cos delta. EF cos delta is this length from this point to this point, right? Which is this point to this point plus this point to this point. So from this point to this point it is Vt, and from this point to this point it is Ia excess sin theta, sine component of this length, isn't it? Vt plus sine component of this length, which is this length, Ia excess sin theta. Same way we can write EF sin delta, but before that we will modify this expression or express Ia sin theta as EF cos delta minus Vt by xs. Ia sin theta equal to EF cos delta minus Vt divided by this xs. Okay, and now we will write EF sin delta. So what is EF sin delta? EF sin delta is this length, which is cosine component of this length, right? So that is Ia excess cos theta. From here we will write Ia cos theta. So Ia cos theta equal to EF sin delta by xs. Okay. Now using these two expressions we will find the power angle characteristic or power angle equation. So in case of any three-phase system, power is given by √3 Vt Ia cos theta. We will consider single phase power, because this phasor diagram is based on single phase. So the total per phase apparent power delivered is S equals to P plus JQ. That is complex form of power. S is volt ampere, P is active power, Q is reactive power. Okay. So here this volt ampere is calculated taking Vt into Ia star. Ia star is complex conjugate of current. So while calculating this volt ampere, we should take complex conjugate of current. Okay. So doing that, we can write that Vt angle 0 degree, here Ia is minus theta, so we have taken plus theta here, because that is the complex conjugate. Okay. So from there we can write Vt cos theta plus Vt sin theta, isn't it? So from this equation, if we compare this one and this one, we can see P is equals to Vt cos theta and Q equals to Vt Ia sin theta. Okay. So therefore active power delivered by the alternator is given by P equals to Vt Ia cos theta, and if we put Ia cos theta equal to this in this equation, we get EF Vt by xs sin delta, right? So that is the power angle equation, variation of power with respect to power angle or torque angle delta. So that is P equals to PM sine delta, where PM equals to EF Vt by XS. Very known and popular equation. So that is the peak active power delivered. Okay? And also we can find the expression for reactive power. So reactive power is Vt Ia sin theta. We have this expression Ia sin theta equal to this. So put this in that equation. Sorry, this will be Q, not P. A typing error. Sorry. Okay. So Q equals to Vt by XS EF cos delta minus Vt. So that is the reactive power calculation formula. So this is for cylindrical rotor machine. And if we plot this P equals to EF Vt by XS sin delta, what will be the plot? It is a sinusoid, half sinusoid. So active power P equals to PM sin delta. If we plot, we will get a plot like this. This is power angle characteristic for cylindrical rotor machine. This plot is very important to define the stability limit, transient stability. So you know the criteria, that is equal area criteria, etc., taught in power system. Okay, so that is not included here. So this is the power angle characteristic for cylindrical rotor machine. So when this power will be maximum, when delta equals to 90 degree. Okay, and reactive power equation remains same. So the above expressions for both active and reactive power delivered by an alternator will remain same with leading power factor load. So we have considered lagging power factor and derived these expressions. If we consider leading power factor load, we will get similar expressions, no change. Now the expressions for same for salient pole type machine. So here also we will neglect the armature resistance, and the modified phasor diagram is this. Okay, so you can see there is no resistive drop here, only two reactive drops. Okay, so the total per phase active power delivered by the alternator, we can write this equation: per phase active power delivered by the alternator, that is Id into Vt sin delta plus Iq into Vt cos delta. Active power means the component of either current or voltage that has to be along the same line. If we consider one as the reference, we have to take the component of other one along that reference one. So if we take Vt as the reference phasor, we have to find the component of Ia along that Vt. If we take Ia as the reference phasor, we have to find the component of Vt along that Ia reference. Okay, so that is the concept here. So here Id and Iq, two active currents are there. So Vt sin delta, see Vt sin delta, which component is this? This component. Is it? Sorry?
Vt sin delta, red dotted.
This one, AB.
B.
So that component into this ID, they are along the same line. So length AB and this ID, that will give you the active component of current due to ID, and Vt cos delta, that is this component into the current along the same line, that is Iq. So Iq Vt cos delta. So that is the active current for this salient pole machine. Okay. Now from phasor diagram, Vt sin delta. What is this Vt sin delta? Vt sin delta is this AB, which is equal to this DC, which is equal to Iq xq, and from there we can write this Iq equals to Vt sin delta by xq. Iq xq equal to Vt sin delta, therefore Iq equal to Vt sin delta by xq. And for Vt cos delta is this length, which is equal to this length OD minus AD. What is this OD? OD is EF. What is this AD? AD is BC, which is XTID. So here Vt cos delta equals to EF minus IDXD from there we can write id equals to this Vt cos delta minus, sorry, EF minus Vt cos delta divided by xd. So we can write in this way. So now we have both the current components, this id and this iq. So putting all these values in this equation and simplifying, we will get this expression. So this is the power angle equation for salient pole type machine. So here you can see there are two components. One is varying with a frequency of delta, another is varying with a frequency double that delta. That means 2 delta. Okay, so two components will be there. So if we plot, we will get a curve like this. So this one is having a frequency of delta, we can say. This one is double that frequency. That means within half cycle of this one, you will have a full cycle of this one. Okay, and if you take the resultant, or if you add these two curves point by point, you will get this curve, which is the actual power in case of salient pole type machine. Okay, now this one PS, that is actually this one, which is equivalent to power to that of cylindrical rotor machine, where XD will be equal to XS only. Okay, so that is called synchronizing power. And this one, you can see this one is independent of EF. It depends on Vt only, Vt and delta and other this reactances. Okay, and that is called reluctance power. Why it is called reluctance power? It depends on reluctance principle only. That means if we run this machine as a motor and suddenly this field excitation get disconnected, then what will happen? This machine will continue to rotate as a motor, where this reluctance power will generate reluctance torque, and that will drive the motor. Okay. So the two components are, this is synchronizing power and this is reluctance power, and also we can write the reactive power as like this. Okay. So any doubt, any question? No question? Okay, so that's it. Any question? Any feedback? How the session was?
Very nice, excellent.
Any value addition to your knowledge after attending this session? Yes?
Yes, sir. Yes.
Excellent, sir.
Okay, thank you, sir.
Sir, can you provide that PPT, sir?
I will mail to Pawan and he will provide you. You have one common group, I think.
Yes.
He will provide you.
Sir.
Yes.
Sir, wonderful PPT you have produced, sir. Thank you so much. We're delighted to have, sir.
Okay. Give me pen drive.
So what is the basic group you are talking?
I gave you two.
PS Vibra.
No, that first one. Latchdog.
Okay.
Then PS Vimra, NGSA, and some other books are also there. Like one book is there, written by some professor Bhattacharya and one professor Shivaji Chakraborty. He is from Jadavpur University. He was a director in NIT Calicut few years back. Bhattacharya Chakraborty. That book is very good.
So these presentations you have made, these animations and all those things, how did you make those?
For that you have to work hard. There are so many sites where you will get this how to do these animations. but directly you will not get. First of all, you have to draw many diagrams either in Paint or in any other software.
All those phases,
For different instants of time.
Okay.
And then that animation site will combine them to form a GIF.
Okay, means like
One instant,
tracing,
two instant,
okay.
instant. In this way, you have to draw all those figures first. Then you have to combine going to that site.
So first you have to draw everything at once, and then one thing you have to draw, one phasor. Then you have to combine. In the PPT it will be implemented. There are websites for that.
Where is focus problem? We have to write. I have to
Yes,
write.
yes.
So let us go to that through. Okay. Thank you then. Thank you. You will have one session with lab. One session will be lab, and then all will take that lab. Whatever experiments I have discussed, those will be demonstrated in the recordings. How this open circuit test is performed, zero product characteristics. Once you have to know how to perform these experiments, from there you will learn. Actually, whatever syllabus I have covered, that is theoretical part. Next is coming all those synchronization, parallel operation. Those are more practical scenarios. That will be for some other course.
And most expression that is I am doing in time phase. I am not practiced in space phase. So for which move I have to follow?
Delay. You can follow this lecture book. First,
second has a sign.
they are
So either in a round, using the time phase.
no.
So what I am interested to practice the
While you will be discussing this voltage regulation, there you will require this specific
space phase.
in relation with the time. Otherwise, if you ask your student to draw the phasor diagram, definitely they will draw the time phasor diagram only.
How many time is it?
Second have sign ready person. It photo group.
Photo.
Excuse me.
पावर के पावर ये केबल रखा
motive করে তাকে পড়তে করে
ठीक है, अच्छा सर, थैंक यू, जय श्री राम। थैंक यू सर, आपकी कृपा से सर अच्छा मैं जीवन में कभी देखा नहीं, बहुत ही अच्छा है सर, बहुत अच्छा सर, कृपया हमें दे दीजिएगा
क्या लिखना है, कहाँ लिखना है?
लाइट ऑन करो।
नाम
ये सर जो है भर दीजिए।
पर्पस ऑफ विजिट,
সেটা ମୁଁ ଆପଣ କାଲି ବି ଜଏନ୍ କରିବେ ତ ସେଇଟା ମୁଁ ଆମ ଟିମ୍ ସହିତ କଥା ହେଇ କହିବି। ଆଚ୍ଛା ଠିକ୍ ଅଛି, ଆପଣ ଏଇଠି